7.5 Proportions in Triangles. The objective in this lesson is to use the side splitter theorem and the triangle angle bisector theorem. These sound like fun. Let's take a look at our first theorem here. The side splitter theorem, guess what's going to happen? We're going to have something that splits our sides. Says if a line is parallel to one side of a triangle and intersects the other two sides, then it divides those sides proportionally. So let's take a look here. I see a line that is parallel to one side of my triangle, and it divides. This is not a midpoint. It could be, but it does not have to be a midpoint. Not a midpoint. It divides the sides proportionally. So what does this look like? This says that segment XR here compares to segment RQ, and segment YS compares to segment SQ. So my sides are broken up proportionally. Don't forget that a proportion is just a foursquare. There's my two left segments and my two right segments. And so we can write a proportion from that. Now, can you guess how this works? It's a theorem, so it's proven. We have parallel lines here. So, parallel. And do you see the transversals cutting these lines? Well, what do we know about parallel lines? Special angle pairs. Which special angle pairs do you see in this triangle? I see corresponding angles on that transversal and corresponding angles on that transversal. So these triangles are obviously similar. And that's how it works. You can read through the proportion or through the proof, and you see the proportions here, seeing that we're using a segment addition postulate, and that adds up the entire side. Because our two triangles are proportional, we have our small one and then our big one, and our big one is made up of this plus this, so that's where that comes in. And then look what we have here on number 6. Do you see one of our proportion rules? Right? We're just adding one. So we can take out this piece and this piece. We can subtract one, and we end up with XR over RQ and YS over SQ. So that's how it works. It's a nice little proof there. More importantly, let's find out how to use our side splitter theorem. Okay, we want to know the value of X in this triangle. Well, how do we know if we're using the similar triangles, or we can use the side splitter theorem? Our requirement was parallel lines. So if we have the parallel lines, that means we can just use the foursquare here, and we can write a proportion. So I can say 12 compares to X plus 1, and 9 compares to X. And then we simply cross multiply. Don't forget to use your parentheses. and then we would distribute. They wrote theirs the opposite direction. Does it matter how we write this? Not at all. We could have also written this as 12 compares to 9, as x plus 1 compares to x. Do we get any different result from this? No, because proportions are way cool. We're still multiplying 12 in x and 9 in the quantity x plus 1. So we do the math and we find out that x equals 3. That means it's your turn. Go ahead and pause the video and do the next two problems. All right, these were some fun little problems. The first one, we were given a triangle, wanted to know the value of A. The line is parallel to one side of the triangle and intersects the other sides of the triangle, which means they are proportional. So I can just draw my foursquare, write my proportion. Don't forget, parentheses, distribute, found A equals 8. So this segment up here is 8 units long. The bottom one is 12 units long. Good to go. Part B, this was a little bit more interesting. We were given triangle XYZ and told that RS joins XY and YZ. R's on XY, S is on XZ. So I just drew that out. Then we're told that segment RS is parallel to segment XZ. So I'm going, all right, I've got, my triangle mid-segment theorem, or not mid-segment. I've got my side splitter theorem. So I know they're proportional. I know that the top chunk and the bottom chunk are proportional. And then it says if YR compared to RX is the same as YS compared to SZ, so that works for me. YR and RX, those we expected to be proportional, and YS and SZ, we expected those to be proportional. But the scale factor is 1. What must be true about RS? The length of RS. Well, if our scale factor is 1, if we have a 1-to-1 ratio, that means they're the same length. So if they're the same length, then they are congruent. And if they are congruent, R and S are the midpoints, and we can use the triangle mid-segment theorem to say that RS, the length of RS, is half of the length of XZ. So that took some thinking and some remembering. Hopefully you saw it, or at least now you're going, ah, yes, that makes sense. Okay, let's move forward. We have a corollary to the side splitter theorem. Corollary means it's a special case. And look at our special case. If 3 parallel lines, and you can have more, if 3 parallel lines intersect 2 transversals, then the segments that are intercepted on the transversals are proportional. So does this sound a whole lot like one of the other theorems we had? Was it a corollary to the trapezoid mid-segment theorem? I think it was a corollary. Do you remember they were in our trapezoid mid-segment theorem, our segments were congruent, which meant that any other transversal, the segments would also be congruent. This is kind of the same idea. We have our 3 parallel lines, and we know that AB is proportional to BC. And if that is true, then WX is proportional to XY. So hopefully you can see that this is the same idea, is that if these were proportional in a 1-to-1 ratio, just like our last problem, they would be congruent, which would mean every other transversal is congruent. So it should make sense to you, shouldn't be too big of a leap, that if our two segments are proportional, then any other two segments on a transversal cutting through these parallel lines will also be proportional. So how do we use this? Proportions are awesome. We use this stuff a lot. So we have 3 campsites on a diagram, and we want to know the length of site A along the river. So we are looking for, in particular, that length right there. Well, what do we know? We know that these lines right here are all parallel. So that means we have proportions, and we can just draw in a foursquare and say that x compares to 8 as 9 compares to 7.2, and we can find out that x equals 10 yards. It's 10 yards long. And it looks like you get to find out the length of side C, or the length of site C along the roadway. So go ahead and pause the video and do this problem. This was a really easy problem. We needed to find the length of site C along the road, and it's just another foursquare because we've got parallel lines. So we had to compare 8 and 6.4 and 7.2 and y. And I just did my proportion, did my cross multiply, and y is 5.76 yards. Now, if you did not use the same proportion as I did, that's fine. I wrote out 3 more possibilities here. I did y to 7.2, which means 6.4 would go to 8, or 8 to 7.2, 6.4 to y, the up and down, just like it's written. Put y on the top, 6.4 on the bottom, so it'd be 7.2 on top, 8 on the bottom. But look at all of these. When I do my cross multiplying, I'm still multiplying y times 8 and 7.2 times 6.4. Proportions are awesome. Okay, that was a good problem. We have the triangle angle bisector theorem. This is a fun one. It says a ray bisects the angle of a triangle. So let's look at this. We have this ray here, and it's bisecting this angle of the triangle. Then that ray divides the opposite side, so side CD here, divides that opposite side into 2 segments. So we've got this segment and this segment. That are proportional to the other 2 sides of our triangle. So we can say CD compares to DB, and CA compares to BA. Now this is just another foursquare, so you can compare them however you like. I tend to do a side and a segment, and a side and a segment. That's just how I see them. Break it up into the foursquare. All right, let's take a look at using this. Find the value of x in the diagram. All right, let's see, what do we see? We are told that segment PQ bisects angle RPS. So here is our ray that bisects our angle. So what can we say? We can say there's our two segments. There's our two other sides. And look at what we have. 10 compares to 18 as 12 compares to x. Cross multiply, x is 21. And it's your turn to do the final problem. Doesn't get much more fun than this. We're asked to find the value of y. I see a bisector of an angle, so I know it's going to split that side into pieces that are proportional to the other two sides. So I marked my proportional sides. If we've got proportional parts, we've got a 4 square. I just wrote my proportion just top left, top right, bottom right. Y is 9.6 is 24 is to 16. You can write that however you like. You could have done the nice 9.6 to 16 is y to 24. However you did it, your answer would have come out to be 14.4 units. So these are some very specific theorems that use proportions. Make sure that you are meeting the requirements, because we've had our triangles that are proportional, but they don't have the parallel line in them. So our side splitter theorem requires that the line be parallel to one side. And then we have the corollary to our side splitter theorem, which has multiple parallel lines, and the transversals have proportional segments. And then we have our triangle bisector theorem, which does exactly what it says. A triangle with an angle that's bisected, and the pieces are then proportional to each other. So these are just special cases of things we've already been doing that makes life a lot easier. So I hope you really enjoy these problems. I think they're a lot of fun, and I think you will enjoy doing them on the homework.